Good morning, students. Welcome in next lecture of Math F242 Operation Research. Audio video is okay. So, in previous class, we have covered the three queuing models: self-service model, single server model, finite capacity single server model. Now, next is the multi-server model. Means we have more than one server in parallel. So presently we are doing the multi-server models, right? So what is the multi-server model? Here we have the S servers. Here we have S servers in parallel. In parallel, and here we are taking means in parallel. What is the meaning of in parallel? Here we have the queue of the customers, and here we have the S servers in parallel. It is the first server, second server, and here we have the S server. So customer will go to any server who are who is idle, right? Who is idle, who isn't any customer. But we assume that there is the single queue. There is single queue in front of the parallel S server system, and all servers have the same service rate or service capacity, or we say that all are providing the service with the rate mu. So this type of the system is known as the homogeneous system. This type of the system is known as the homogeneous system because all the servers are providing the service with the same rate. And from the candle notation, we know that what is the meaning of this. Here we can say we have the infinite population. Infinite population. Here we have the infinite capacity. Infinite capacity. Here we have the Q discipline. Q discipline. So Q discipline we are taking as a first come first serve. As I have told you, this is the number of servers. Then after here we have the service time. Service time follow the exponential distribution with parameter mu, and here we have the interarrival time. Interarrival time of the customer also follow the exponential distribution with parameter lambda. So this is the Poisson queue, right? Poisson, in the Poisson queue, we assume that service time as well as the interarrival time both follow the exponential distribution. Now, when we are talking about the multi-server system, so here we have the MMS FCFS infinity system. So in this case, initially there is no customer. Initially there is no customer. The first customer arrive with the rate lambda. Then second customer arrive with the rate lambda. Similarly, n minus 1, n, n plus 1, s minus 1, s, s plus 1. Then after n minus 1, n, n plus 1, and so on. So here the nth customer arrive with the rate so here we have the lambda s, and it is continue because the capacity is infinite, population size is infinite. So here the rate is the lambda n minus 1, and lambda n and so on, and up to the infinity it will go. Now please pay attention. when we have when we have only the one customer, so only one server is busy, and the customer will get the service with the rate mu. If there are the two customers, right, if there are the two customers, then two servers are busy and they provide the service with the rate 2 mu. Similarly, if there are n customers, then they provide they get the service from the n servers with the rate n mu. If there are n plus 1 customer, they will get the service with, from the n plus 1 servers with the rate n plus 1 into mu, and so on. If there are s customers, all the s servers are busy now for providing the service to the all s customers with the rate s mu. Now if we have the more customers, since we have the limited number of the server, so all server are busy and they provide the service with the rate s mu, s mu and s mu. This assumption is clear. It means we have lambda n is equal to lambda, right, for n is equal to 0, 1, 2 and so on, and mu n is equal to n mu when n is equal to 1, 2 or s minus 1. If it is the n is equal to s, if n is equal to s or s plus 1 or more, then it will be the s mu. This assumption is clear, because this is the only the difference from the mm1 and single server and this server multi server model. Any doubt to understand why I am taking the n mu and s mu?
Sir, why have you taken SMU?
Why? Please repeat.
Why did you take SMU?
S mu because there is the S server, and during the Poisson distribution, I have told you the service time or any distribution. During the probability distribution, I have told you if the x1, x2, xn follow the Poisson distribution, then their addition also follow the Poisson distribution with parameter mu1 plus mu2 plus mu1. So here we have the S server. First server is providing the service. First server provide the service with the bit service time which follow the exponential distribution. Right, exponential distribution. Here it follow the exponential distribution. Here we have the exponential distribution. Their means their server, how many services it provide, right, that follow the Poisson distribution. So their rate we add. So here we have the mu, and mu. So if we have the n server, so it provide the service with the rate n mu. Means the service rate will add. Only main thing is the service rate will add. Now maximum we have the S servers. So due to the S servers, here we have the S mu. Whether we have the S customers, S plus 1 customer, S plus 2 customer or more customers. Because we have the S servers only, so maximum the service rate will be the S mu. If there are the less customer, then we have the service with the rate N mu. Whatever the number of customers, that much server will be active to provide the service.
Okay. Thank you.
So that I have made in the transition diagram also. So from the transition diagram, you know, we can write easily the Chapman-Kolmogorov differential difference equation. Chapman-Kolmogorov differential difference equation. So for the first node, if you write dp0 by dt is equal to whatever the outgoing, that is with the negative sign, lambda p0t plus mu p1t. For the nth node, d pnt by dt, so it will become minus lambda plus n mu pnt plus lambda pn minus 1 t plus n plus 1 mu pn plus 1 t. And here n vary from 1, 2 and up to the s minus 1. So here you can see up to the s minus 1 we have the same trend, right? Here we have the lambda, means this is equal to lambda, this is equal to lambda, all the lambdas are the lambda, all the lambdas are lambda, right? So here we have the, this is the outgoing with the negative sign lambda and mu, and this is the incoming, with the positive sign. So up to the s minus 1 we have the same trend. Now if you write the equation for more nodes, so here we have the dpn by dt is equal to minus lambda plus s mu pnt plus lambda pn minus 1 t plus s mu pn plus 1 t for n is equal to s plus 1, s plus 2 and so on. So here we have the, you can see from the transition diagram, for this node to onward, right, to onward we have the same trend. So outgoing will be the negative with the negative sign and incoming with the positive sign. And here we require the initial condition. So initial condition will be that at t is equal to 0 we have the 0 customer, its probability is 1. At t is equal to 0 we have the more customer, is the 0, for n is equal to 1, 2, s plus 1 and so on. So that is the initial condition. From here we can develop the steady state equation. From here we can develop steady state equation. Steady state equation means here we have the minus lambda independent of t. So when independent of t means t tends to infinity and dy dt is equal to 0. So minus lambda plus mu p1 is equal to 0 minus lambda plus n mu pn plus lambda n minus 1 or lambda, not n minus 1, lambda pn minus 1 plus n plus 1 mu p n plus 1 is equal to 0 for n is equal to 1, 2 up to the s minus 1. And here we have the lambda plus s mu pn plus lambda pn minus 1 plus s mu pn plus 1 is equal to 0 for n is equal to s plus 1 and so on. With normalizing condition, what is the normalizing condition? Sum of all probability n is equal to 0 to infinity is equal to 1. Sum of all probability is equal to 1. So here we have the steady state equation. So we can, now we have to compute the state probabilities. So we have the two approach. Either you solve the following system of equation or you follow the steady birth and death process. So by the birth and death process we know that what is the pn is equal to cn into p naught, where cn is what? Cn is the lambda naught, lambda 1, lambda 2, lambda n minus 1 upon mu1, mu2, mu3 and mu1. So this is equal to all the lambdas are lambda, so it is the lambda, lambda, lambda and lambda, and mu's are mu1 is mu, mu2 is 2 mu, mu3 is 3 mu and mu n is n mu. when n is when n is less than equal to s minus 1, when n is less than equal to s minus 1, then we have this. Otherwise, lambda, 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 lambda upon it is mu, it is mu, 2 mu, 3 mu, then s mu, then s mu and s mu, lambda and lambda. Means up to the s, it is the mu, 2 mu, 3 mu and s mu. After that, it is the s mu, s mu, s mu. Clear? From the transition diagram, you can observe this. We have the mu1, mu2, right? mu1, mu2. Here we have the mu n plus 1. Then here we have the s mu or mu s plus 1. Then mu n and mu n plus 1. Clear? So because here it is the important thing to understand. So this is equal to lambda upon mu, we can write as a rho. So it will be the rho to power n upon 1 into 2 into 3 into n. Lambda upon mu, if you assume as a rho, so it will become rho to power n upon 1 into 2 into 3 into n. And here we have the rho to power n. Again, the lambda upon mu is equal to rho. So rho to power n. Here we have the 1 into 2 into 3 into s, then into s into s into s into s. When n is less than s minus 1 and n greater than equal to s, right? When here we have the n greater than equal to s. So this can be written as rho to power n upon factorial n, and this can be written as rho to power n upon factorial s. Now how many s we remain? Up to here we have the factorial s, and how many s now we have? Anyone?
N minus S.
Yes, we have the n minus s, right? S. So that can be written as s to power n minus s, s to power n minus s for n less than equal to s minus 1, for n greater than equal to s. So this is your Cn, and we know that what is the Pn? Pn is equal to Cn into P naught. And from here, from normalizing condition, from normalizing condition, what we have? Sum of Pn is equal to n is equal to 0 to infinity is equal to 1. That is the P naught, P1, P2, Ps minus 1, Ps, Ps plus 1, Pn is equal to 0. This we have. So from all we can, because we have the Cn into P naught. So if you take the P naught common, here we have the 1 plus C1 plus C2 plus Cs minus 1 plus Cs plus Cs plus 1 S plus 1, and here we have the Cn and so on, is equal to 1, is equal to 1. Sum of all probability is equal to 1. And P naught, so up to here, what we have the value of the Cn? Up to here we have the value of the Cn as rho to power n upon factorial n. So this can be written as summation n is equal to 0 to s minus 1 rho to power n upon factorial n. And from here, what is the value of the Cn? If you take the n is equal to s to infinity. For the s to infinity, what is the value? Rho to power n factorial s and s to power n minus s. N minus s, that is the value of the Cn is equal to 1. So this can be written as P naught summation n is equal to 0 to s minus 1 rho to power n upon factorial n. It is the factorial n. Factorial n plus, now from here, if you take the rho to power s upon factorial s outside the summation, n is equal to s to infinity, and here we have the rho to power n minus s upon s to power n minus s is equal to 1. Can you tell me what is the value of this summation? If you put n is equal to s, so what is the first term? If you put n is equal to s, the first term is 1. 1, right? But if you put the n is equal to s plus 1, so it will be the rho by s. If you put the n is equal to s plus 2, it will become rho by s square, and so on. So it is what? It is the GP. It is the GP with common ratio rho upon s, and it is the infinite GP. So this is equal to the 1 upon 1 minus rho upon s. 1 upon 1 minus rho upon s, when rho upon s must be less than 1. That is the lambda upon mu s less than 1. That is the lambda less than mu s. Means effective arrival rate must be less than the effective service rate, right? Effective service rate. That is the required condition. So in this case, this will become P naught summation n is equal to 0 to s minus 1 rho to power n upon factorial n plus, right? This is the first part, and here we have the rho to power s upon factorial s. Then sum of this summation, right? So value of this summation will be the 1 upon 1 minus rho upon s, and it is equal to 1. So from here we can compute what is the value of the P naught. P naught is equal to summation n is equal to 0 to s minus 1 rho to power n upon factorial n plus rho to power s upon factorial s and 1 minus rho by s and its inverse. That is the value of the P naught. So P naught for the multi-server model we compute like this. So after having the knowledge of the P naught, we can compute the Pn as a Cn into P naught. Cn into P naught, and Cn you know what is the value, or you can say it is the rho to power n upon factorial n into P naught, and it is the rho to power s upon factorial s or rho to power n and upon factorial s and s to power n minus s into P naught. So if n less than equal to s minus 1, if n greater than equal to s, we have this value of the Pn. So now after having the knowledge of state probabilities, we can compute the performance measures. So now performance measures. So here we compute the performance measure as probability that all servers are busy. All servers are busy. All servers are busy, or probability of busy period. Probability of busy period. So when the all servers are busy, anyone? Yes, when n greater than equal to s, means it is equal to probability that there are s or more customers. There are s or more customers. That is the probability n greater than equal to s. So that is what? That is the ps plus 1, ps plus 2, and so on. And in this range, what is the value of the Pn? Here we have the summation n from s to infinity Cn into P naught. So Cn is what? Rho to power n upon factorial s to power n minus summation n is equal to s to infinity rho to power n upon factorial s to power n minus s into P naught. And this summation just now we have seen, this can be written as this summation can be written as rho to power s upon factorial s if you take common, right? P naught, we have this summation of rho to power n minus s upon s to power n minus s can be written as 1 minus rho to power rho upon s inverse, right? 1 upon 1 minus rho to power s. So that is the value that is the required probability that all servers are busy. So here, because the P naught expression is little bigger, so we are writing directly the P naught, right? First we compute the P naught, thereafter we put the value of the P naught wherever we require. After that, we compute the LQ. LQ, what is the LQ? Expected number of customers in the queue. Expected numbers of customers in the queue. That is the EQ. Basic formula is what? Summation n from s to infinity n minus s into Pn. N minus s into Pn. That is the basic formula. So this can be written as n is equal to s to infinity n minus s, and what is the value of the Pn in this range? Root to power n upon factorial s to power n minus s into P naught. That we can write here. So if you are writing this, and if you take the root to power s upon factorial s outside, so what is the inside? Right? So first term n is equal to s, so 0. Right? Second term, so it will become 1 into rho upon s plus 2 into rho upon s whole square plus 3 into rho upon s whole cube and plus n into, right, n into rho to power rho upon s to power n and so on. Clear? Clear this part? Why it is coming like this? Is there any doubt? So again, it is the GP series, right? AP GP series. And can anyone, what is the sum of this? I have already covered. What is the sum of this? Let us assume rho upon s as a u. So what will be the sum? If you assume rho upon s as a u, can anyone tell me what is the sum of this summation?
Sir, u by 1 minus u whole square.
Yes, it is the u upon 1 minus u whole square. Right? So this can be, I'm not going in that part again because I have already covered in the MM1 model. So this is the rho upon s upon 1 minus rho upon s whole square. That is the sum of this, and here into P naught. Into P naught. So here we have the into P naught. That is our LQ. So if you put rho to power s upon factorial s, this can be written as lambda mu s upon mu s minus lambda whole square into P naught also. So that is the LQ in terms of the lambda mu, just by putting the value of the rho as lambda upon mu. So that is the LQ. Now, if you have to compute the expected number of BG server, because we have the S servers in our system, right? We have S servers in our system. It is not necessary always all the S servers are busy. Maybe zero server is busy, maybe one server is busy, maybe two servers are busy, maybe S minus one servers are busy, or maybe the all S server are busy. So it is what? It is the EB. It is the EB, and it is equal to number of customers in service, that is the EU, and it is equal to, we know that it is equal to, right, how many server are busy? If there is one customer, one server is busy. If there are two customers, two servers are busy. If three customers, three servers are busy. S customers, S server are busy. So that is the n into Pn, n into Pn, and here n is equal to, we have the n is equal to 0 to s plus summation. If there are s plus 1 customer, then also s server is busy. S plus 2 customers, then also we have the s customers are s servers are busy. S plus 3 customers, then also we have the s servers are busy. So here number of busy server value into Pn, n vary from s plus 1 to infinity. So that will be the basic formula for the expected number of busy server. Expected number of busy server. Basic formula is clear. Why I am writing this? Basic formula is clear, right? Because here we have taken the npn plus spn. So for the first range, for the first summation, we know that what is the pn? Pn is summation n is equal to 0 to s, n is equal to 0 to s n. And for the first sum, we know that it is the root power n upon factorial n into p naught. Pn is equal to this, plus summation n is equal to s plus 1 to infinity. Here we have the s, here we have s, you can take outside. What is the Pn for this range? Here we have the root power n upon factorial s to power n minus s into p naught. That is our Pn. So if you cancel this n, here we have the, or in next line you do. So here we have the n is equal to 1, because in first line why we cannot do? Because here n start from the 0. So when the n start from 1 to s, then you can say that it will be the root power n upon factorial n minus 1. Factorial n minus 1 into p naught. N and 1 n we cancel. So here we have to start the summation from the n is equal to 1. Then here also summation we have n is equal to s plus 1 to infinity. If you cancel this s with here, so here we have the root power n upon factorial of s minus 1, right? S to power n minus s into p naught. Clear this part? Now this can be written as, if you take the row common, so inside we have n is equal to 1 to s row to power n minus 1 upon factorial of n minus 1 into p naught, plus if you have taken already, you have taken the row common, so here we have the n is equal to s plus 1 to infinity, and here we have the row to power n minus 1 upon factorial of s minus 1, right? And here we can write s to power n minus 1 minus s minus 1, and here we have the p naught. Now if you replace n minus 1 by the m, if you replace the n minus 1 by m, so this will become row summation. Now this summation will start from m is equal to 0 to s minus 1, right? Because here the summation is equal to n is equal to 1 to n is equal to s, n is equal to s plus 1 to n is equal to infinity. So here we can write this m is equal to s to infinity. M is equal to 0 to s minus 1, right? And here we have the row to power m upon factorial m p naught, plus here we can write row to power m upon factorial of the s minus 1, factorial of s minus 1, and s2 power factorial of s minus 1, s2 power m minus s minus 1, m minus s minus 1 into p naught, So what is the what is this? This is the pn row. So this is the summation m is equal to 0 to s minus 1, and this is the pm, right? This is the pm plus what is this? M is equal to s2 infinity. So what is this? This is also a pm. This is also pm, right? Just for the different range. So m is equal to 0 to infinity. M is equal to 0. This is the row, and this will become m is equal to 0 to infinity of pm. What is the bracket? Sum of all probability. What is the bracket? Sum of all
1.
probability. 1. Right? So this is the row. This is the row, right? Because it is the sum of all probability is equal to 1. So that's why rho is known as the utilization factor, because here it give you how much how much the service facility you are utilizing. So that's why it is also known as the utilization factor. Rho is also known as the utilization factor because it give you how much you are utilizing your service facility. Now, so few performance measure we have computed. Now next is the important one. What is the L? L is the EN. EN is what? Expected number of customers in the system. Expected number of customers in the system. And we know that what is the L? It is the EQ plus EU. EQ plus EU, number of customer in queue plus number of customer in service, which can be written as, or you can say, if you have the confusion, N is equal to what? Q plus U. Then EN is equal to, EQ plus EU. And just now we have computed the EU is nothing, it is the EB. It is the EB, and EQ we have already computed as a LQ, and EB already we have computed as a rho. So here the L is equal to LQ plus rho. So here need not to write the explicit expression. Directly you can write, or if you want, you can put the value of the LQ as a rho to power s upon factorial s lambda mu s upon mu s minus lambda whole square into p naught plus rho. So that is the value of the LQ. Then after L, and that is the value of the L. Then after we have the lambda bar. Lambda bar is what? Effective arrival rate. So effective arrival rate is the what? It is the lambda n into Pn for n is equal to 0 to infinity. That is the basic formula. And for this model, we know that all the lambdas are. For this model, we know all the lambdas are lambda. So it is the summation n is equal to 0 to infinity lambda into Pn. That is the independent of n. So lambda and n is equal to 0 to infinity Pn. So it is what? This summation is 1, right? This summation is 1. So it is equal to lambda. So here the lambda bar is equal to lambda for the multi-server model. Then after we have to compute the W. W is what? It is the expected waiting time. Expected waiting time. Expected waiting time means it is the E of t, E of t, and by the little formula, it is equal to L upon lambda bar. So L already we have computed as a L, and here we have the lambda. Similarly, WQ is what? E of TQ, E of TQ, and E of TQ means it is the LQ upon lambda bar. So LQ already we have computed, and here we have the lambda. So in this way, we can compute the expected waiting time in the queue. It is what? It is the expected waiting time in the queue. In the queue. This is the expected waiting time in the system. In the system. So in this way, we can compute all the performance measures. Clear? So that is the multi-server model. So next class, we continue with the numerical example. Means now we will do the numerical for all the queuing models so that you can recognize which model we have to apply. So we have the two more queuing models. So after that, we will do the all the numerical examples. So in next class, we will do two remaining queuing models. Then after we start the numerical example. So that's all from my side for today. If you feel any doubt, please ask at any point. During the derivation, during the formulation.
Thank you, sir.
Welcome.